In this video I will show you how you can monitor your pet or a self-made nesting box for less than 10 euros with the help of an ESP32 cam microcontroller. As you can see, I am currently still looking for a tenant. I'll also show you how to use a Raspberry Pi or a Linux-based server to regularly grab an image for the ESP32 cam and assemble it into a time-lapse video. However, for the image quality of this video I use the Raspberry Pi HQ cam, but the underlying principle is always the same. For this video I assume that you have the Arduino IDE installed on your computer. If you like to save the pictures regularly on your server and have them processed to a time-lapse video, you also need a Raspberry Pi or Linux-based server. You will also need an ESP32 cam microcontroller, which is currently available on eBay or AliExpress for about 6 euros including shipping. To be able to program it, you also need a USB to TTL converter like this one. First we connect the cables from the ground, 5 volts, RXD and TXD to the USB converter. I use the black for ground and red for 5 volts. The R in RXD stands for receive and the T in TXD for transmit. These must be connected crosswise at the ESP. To make sure that the ESP32 doesn't boot normally, but starts in programming mode after power on, it is also necessary to connect the pin IO0 to ground. You can now connect the USB to TTL converter via USB to your computer and continue with the software programming. First we enter the shown additional board manager URLs in the preferences of the Arduino IDE. You can also find the links in the video description. Then we make sure that under Tools, Boards Manager, the ESP32 boards from Espressif are installed. This is already the case for me, so I only have the Remove button here. Now, under File, Examples, ESP32 Camera should be the camera web server example, which we now open. There we have to enter the SSID and the password of our Wi-Fi network. We also have to select the correct camera type. In my case, this is the AI Thinker model. So we change the double slashes in the appropriate places. Now we can compile the file and upload it to the ESP32. We do that under Tools, Board, ESP32 Arduino, AI Thinker ESP32 Cam. After checking if the correct COM port is set for the USB converter, we can press the upload button. If there is no connection during the upload, you have to press the reset button on the board. If you use a breadboard like me, you can't reach this button. That's why I unplug the 5 volts cable and plug it in again. Now the upload should start. I sped up the video here a little bit. Now we can remove the bridge cable between pin IO0 with ground and reset the ESP32. If you start the serial monitor in the Arduino IDE, the boot process should look like this. Once the ESP32 has booted up, it will display the IP address that the router assigned to it. Now you can also remove the receive and transmit cables and run the ESP32 only with 5 volts and ground. If we enter the IP address of the ESP32 in the browser, we get its interface and can shoot the first test images. When we click on the Start Stream button, we can already transmit a first video image. By the way, some internet users report that the connection is interrupted again and again when the ESP starts up. The error message in the serial monitor then refers to a brownout detector. It can help if there is a slightly increased voltage of about 5.5 volts. If this is not enough, you can solder an additional electrolytic capacitor and a ceramic capacitor between ground and 5 volts to get a better coverage of the voltage peaks during booting of the microcontroller. With this, the power supply should be stable. If you want to use the ESP32 cam for your projects and you are quite satisfied with the example project, I would still recommend a few optimizations. If you use it continuously, you will soon notice that the microcontroller stops working if the Wi-Fi signal is interrupted for a short time. In order not to have to reset the hardware regularly by hand, we add an ESP restart in the code if the Wi-Fi is not found after a few seconds during the boot process, and we add a similar check to the loop which checks again and again if the Wi-Fi connection is still up. With this, the project should now be ready for continuous operation. By opening the IP address with a /capture command, you can get the current image of the camera without having to go through the interface. With /status, you get the current settings as a list. You can change each parameter by typing /control. Here I did it, for example, for the image quality. The next time capture is called, the image will have a lower resolution. And with control, I reverse this and get the original size again. So you can take the modifiable attributes from the status overview and simply change them according to the shown scheme. Thus, we are able to write a simple Linux script that brings the ESP into the desired settings and write an image via wget to our server. If we now call this script with a simple cron job, for example every minute, there is always a current image in the specified folder. I have refined the script a bit, but the basic principle is still the same. First, I want 3 pictures to be taken per minute. I add a timestamp to the file name. Now, under the variable latest, the name of the latest file is stored. And just in case the ESP has reset itself, the settings are sent to the microcontroller over again. Now I create a watermark with the current date and time on the image and save a copy of it on my web server. As you can see, the main folder with the timestamps fills up with the images after a while. With the second bash script, I now let daily or hourly convert the pictures to a video. For this, I write the file names into a text file and then convert them with mencoder into a H.264 file. Then I convert it with FFmpeg into a MP4 and a WebM video and delete the JPEGs, though that the server doesn't run over. By the way, you can find the examples on my GitHub account, which is linked in the video description. For applications like the nesting box, it can be helpful to use infrared LEDs for the illumination. With this, as in my example the birds, can be observed undisturbed during the day and night. Here again, the time-lapse video in daylight and sunshine. To make the ESP32 cam sensitive to infrared light, it is necessary to remove the infrared filter of the lens. So if you are feeling lucky, you can try to peel off the front of the camera with a knife to take out the infrared filter. After that, shots with both 940 and 850 nanometers work great. I also just used this infrared modification on another project where I used an ESP32 cam as a front doorbell camera. Of course, it should be clear that the removing of the IR filter makes the images look almost black and white. But for many purposes, this doesn't matter too much. You see, the ESP32 cam can be used for many purposes. Together with the shown scripts, it is especially useful for entertaining time-lapse videos which you can enjoy day by day. If you liked my short tutorial, subscribe to my channel and give me a thumbs up. And don't miss my next video when I show you how to use the ESP32 cam for AI supported reading of your water meter.